We're in section 5.4, indefinite integrals and the net change theorem. In the previous section, we saw that the fundamental theorem of calculus part 2 is a very powerful method for evaluating the definite integral of a function, assuming that we can find an antiderivative of the function. In this section, we learn about a notation for the antiderivative, review the formulas for antiderivatives, and then use these formulas to evaluate definite integrals. So an indefinite integral, this is different than what we just talked about in 5.3. An indefinite integral is a general antiderivative. It's also called an indefinite integral. An indefinite integral notation is the integral of f of x dx is equal to capital F of x plus c, which means capital F prime of x is equal to f of x. All that I want you guys to really realize here is that that integral has no values on it. It has no lower bound and no upper bound. And when we have this kind of integral, this indefinite integral, you need to add a plus c to your ending antiderivative. So the first one that we have is evaluate the integral of 2x cubed minus, and I'm going to rewrite that as x to the 1/2 plus 3 dx. And we're going to go term by term by term and taking the derivative of, or the antiderivative of each one. And so we're going to take the 2 out in front, that's just a constant. I'm going to add 1 to my exponent and divide by that same number, minus, add 1 to my exponent and divide by that same number. Again, if you prefer, you can rewrite this as multiplied by the reciprocal, plus 3. And there's no value there. So if you think about it as x to the 0, that means that we would add an x, and you could say you would add an x to the first and divide by 1. I also need to remember to always add my plus c. So from here, this simplifies to 1/2 x to the 4th minus 2 over 3, and I'm going to write this as the square root of x cubed, plus 3x plus c. And this would be your final answer. What's nice with antiderivatives is that you can take the derivative and actually check to see if you did this correct. So if you have time on your exam, you can always take a derivative, double check that you did it correct. B, a little bit different. We have to think about it a little bit different. We will work on that one together in class. So note the integral of f of x times g of x is equal to, not equal to, the integral of each of those. And same with the derivative, or dividing, it's not equal to. You can't distribute an integral. So I want you guys to realize that those are not equal to. So the next example that we have says evaluate, and this is the integral of 2x to the negative 3rd plus e to the negative x plus secant squared of x minus 1 over 1 plus x squared dx. So we're going to go term by term by term. So the first one is going to be, we have 2 times, I'm going to add 1 to that exponent, so this is going to be x to the negative 2nd all over negative 2 plus e to the negative x is going to be e to the negative x divided by negative 1 plus the antiderivative of secant squared is just tangent of x minus, and then looking at your formula sheet, 1 over 1 plus x squared is equal to tangent inverse of x. And then again, since this is an indefinite integral, we are going to add that plus c. From here, see if you guys can clean this up. We should end up with the negative 1 over x squared minus e to the negative x plus tangent of x minus the inverse of tangent of x plus c. And that would be your final answer. If you wanted to, you could rewrite that e to have be in the denominator. So for b, we're going to go ahead and take the antiderivative of each of these terms. This is, again, an indefinite integral. For the first one, though, if you want to think about this as 3 x to the negative second. Makes it a little bit easier to take the antiderivative of. So doing it that way, we're going to have 3 times x to the, adding 1 to your exponent, it's going to be negative 1 over that same value, negative 1. And then it's minus 3 times e to the 2x. Instead of times 2, it's dividing by 2 since it's the antiderivative. Plus, we have sine is going to be negative cosine of 3x divided by 3. And again, you can always check this. Take the derivative of that term if you're having a struggle with it to see it. And then the antiderivative of 3 to the x is going to be plus 3 to the x all over ln of 3. And then this is an indefinite integral, which is going to be a plus c added to it. Checking this, you can always take a derivative of this and see if it matches to what we have as our original function. But from here, I'm going to go ahead and clean this up, and we have negative 3 over x minus 3 over 2 e to the 2x minus 1/3 cosine of 3x plus 3 to the x ln of x over ln of x, or ln of 3, sorry, ln of 3 plus c. And that would be our final answer. So for c, we will go ahead and leave c, and we will work on that together. So common mistakes are listed on there for you guys to look at on your own. Here are our main ideas. And it also says we want to use integrals and the area interpretation as a way of computing net change or total change. One example is to find the total distance traveled. We saw this back in section 5.1. The net change as an integral of a rate is the integral from t0 to t1 of the rate of something equals the net change in something between t0 and t1. The net change in q of t, the quantity over an interval of t0 to t1, is given by the integral. The integral from t0 to t1 of q prime of t dt is equal to q of t1 minus q of t0. We can also use the formula in a different way, and it's rewritten down below, moving around those terms. Note the rate will not be always given and using derivative notation. First example on here says the number of cars per hour passing an observation point along a highway is called the rate of traffic flow, or C of t, in cars per hour. Which quantity is represented by the integral from t0 to t1 of C of t dt? So we have a few things going on in our integral. So let's go ahead and look at that before we can actually discuss this. So we have C of t and we have dt. So C of t, they said, is the rate. And this is cars per hour. And then d of t up here is the change in times. This is our time. And we're measuring time in hours. So the integral from t0 to t1 of C of t times dt is going to be written as, or explained as, it represents. This is the total number of, and if you were to multiply cars per hour times hours, we get the total number of cars passing an observation point and that was the observation point between the time t0 and t1. The flow rate in cars per minute is recorded in 15-minute intervals between 7 and 9 a.m. Estimate the number of cars using the highway during this 2-hour period by taking left endpoints. So make sure you guys notice it does say left endpoint approximation. So if you start with your left endpoints, the number of cars, and if you want to think about it as a graph, you can totally make a graph. And I don't want to make the whole graph, but we can do part of it. This would be your time intervals. And so it starts at 7. So go to make this be 7. This would be 7:15. We have 7:30, 7:45. And I'm just going to leave this and say dot, dot, dot. Okay, our vertical axis is going to be C of t, which is that rate of flow of cars. And from here we have first interval is going to go from 7 to 7:15, and there was 1,044 cars. The next interval is going to go from 7:15 to 7:30, and there was 1,297 cars. And then the next interval again is even higher, and dot, dot, dot. You're figuring out these heights based upon the left endpoint. So from here we have the number of cars is approximately. So number of cars. And again, it's approximately. And the reason why it's approximately is because this is 15-minute intervals that we're looking at. It's an approximation where you're using rectangles to kind of approximate that total area. So we have the first interval, which is 15 minutes times the number of cars that we see, which is going to be 1,044, plus the next 15-minute interval times 1,297 cars, plus 15 times the next interval, which is 1,478, plus, and continuing on this process. And then the only thing is we need to look at is that last interval, because we are using left endpoints. We're not using the right endpoint. So the last interval, that last height of that rectangle is determined by the 802, not the 542. So if you were to add these, multiply this up, add this all up, sum it, you're going to get a total number of cars was about 156,735 cars. And this is between 7 a.m. and 9 a.m. Again, if it helps to draw out that table as a graph for the whole thing to look at and get a better idea of what's going on, definitely do that. The next example that we have on page 16 says a survey shows that a candidate for mayor is gaining votes at a rate of 2,000 T plus 100 or 1,000 votes per hour, where T is the number of hours since voting began at 7 a.m. How many votes will the candidate have at the end of the voting period at 8 p.m.? Assuming that at T equals 0, she had an initial 30,000 absentee ballots. So we have, how many hours was voting open? So voting was going from 7 a.m. until 8 p.m. So that's a total of 13 hours of voting. So when we look at the total number of votes, at time 0, she started with 30,000 votes. And that was that absentee votes. Plus, and then she was getting votes at a rate. And since we have a rate, we need to integrate that to figure out the number of votes. And so we're going to have the integral of that function, which is going to be 2,000 T plus 1,000, and then dt. And this is being integrated for those 13 hours, not from 7 to 8, because that's not, in terms of time, time is starting at technically when the pole station opened was at 0, and it closed 13 hours later. So there's 13 hours there, not just 1 hour if you went from 7 to 8. So working this out, we're going to have our 30,000, that's just a constant that stays there. That's nothing to do with the integral. And then we have our integral, which is going to be the 2,000. We're going to put t squared all over 2 plus 1,000 t. And this is going to be evaluated from t equals 0 to 13. And then from here, we get our 30,000 plus, and then if you evaluate this at 13, we're going to end up with, and you can simplify that as 1,000. So we're going to end up with 1,000 times 13 squared plus 1,000 times 13 minus, and if you were to substitute in 0, you just get 0. So I'll write 0 there. And then working this out, you're going to end up with 212,000 votes. So they use this kind of idea when they say, oh, looks like this candidate is going to win because they're getting votes at this kind of rate. So very useful in the political field. Okay, displacement versus total change traveled, or total distance traveled. It says if an object travels in a straight line with a velocity of v at t, then displacement during t0 to t1 is the integral from t0 to t1 of vt dt, which is going to be equal to the integral from t0 to t1 of s, which again was our position function, the derivative of that, and that's equal to s of t1 minus s of t0. The total distance traveled from t0 to t1 is equal to the integral from t0 to t1 of the absolute value of v of t dt. So there's a few examples left, and we will work those out together in our mini lecture. But go ahead and take some time to kind of look at those and see if you can understand them before we get into them, because they are word problems, a little bit more of an understanding that is going to be needed.